Point a camera at a street, a person, two cars, a dog, a traffic light. You want a program that draws a box around each one and names it. That is object detection. Here is why it is hard. Ask a program, is this a picture of a cat? And the answer has a fixed shape. One picture in, one word out. Ask it what is in this picture and where, and the answer has no fixed shape at all. There might be nothing. There might be 40 things at 40 different sizes, half of them hidden behind each other. The program has to decide how many answers to give before it can give any of them. 25 years of work on that one problem. And the timeline is not a list of clever people. Every era exists because the era before it hit a specific wall. I will name the wall every time. 2001 to 2026. You need to output a list, and you do not know how long the list is. In 2001, nobody knew how to make a program do that. But they did know how to make one answer a fixed question. Is there a face inside this small square? Yes or no? That is a classifier, and classifiers worked. So the field made a trade. Turn the hard question into the easy question, repeat it. Take a small window, slide it across the image, a few pixels at a time. At every position ask, is it here? Then shrink the image and sweep again, so a face filling the frame and a face 40 pixels wide both get caught. That is the sliding window, and the cost is brutal. One modest photograph gives you well over 100,000 windows. So your classifier does not need to be good. It needs to be good and run 100,000 times on a computer from 2001.
2001. Paul Viola and Michael Jones publish a face detector that runs in real time on the hardware of the day. 3 ideas, all about avoiding work. First, the features are insultingly cheap. Take a rectangle, split it in 2, subtract the brightness of one half from the other. That is the whole feature. The eye sockets are darker than the cheeks. Second, the integral image. Build one table up front, and after that, the total brightness of any rectangle at any size costs 4 lookups. 4. Size stops mattering. Third, the cascade. Nearly every window is background, so do not run the full detector on all of them. Put 2 cheap features at the front and throw most of the image away immediately. 15 frames a second on a 700 megahertz machine, and the wall is already visible. Those rectangles were designed by hand for fascias. Want to find a car? Start over. 2005. Navneet Dalal and Bill Triggs go after pedestrians, and light versus dark rectangles do not survive contact with a person. There is no reliable bright patch anywhere on us, and our clothes change color every day. So change what you measure. Not brightness, but the direction brightness changes in. At every pixel, work out which way the image is getting darker and how fast. That is a gradient, and gradients run along edges. Chop the window into small cells, and in each cell keep a count of which gradient directions showed up. Then normalize across neighboring cells, so a bright day and a dark day give the same answer. That is a description of local shape that ignores color and lighting. Histogram of oriented gradients, HOG. Feed it to a support vector machine, a simple classifier that draws one dividing line, and pedestrians start working. Still a sliding window, though, and still one rigid template, which is fine, right up until the person raises an arm.
2008. Pedro Felsenswalb and colleagues answer that directly. Objects are not rigid, so stop modeling them as one shape. A deformable part model has a root filter, the whole object at low resolution, plus part filters at higher resolution. A head, a shoulder, a leg. The parts are allowed to move relative to the root, and moving costs you. It is a spring. The score is what the parts found, minus a penalty for how far they had to stretch. The clever part is the training. Nobody labeled where the head is. The dataset only has whole person boxes. The model discovers the parts by itself. This won. Deformable part models dominated the Pascal competition for years, the last champion before deep learning. And it is where the era runs out of road. For a decade, the best people envisioned hand-designed features, and the benchmark crawled. The bottleneck was never the classifier. It was that a human being was choosing what the computer was allowed to look at.
2012. AlexNet wins the ImageNet competition, and it is not a detector at all. It is a classifier. One image in, one label out. But it moves the numbers so violently that everything downstream gets rebuilt. The error rate drops from around 26% to around 15%. And the important part is not the accuracy. It is where the features came from. Nobody designed them. When you look at what its first layer learned, it is edges at different orientations. Roughly what HOG was measuring by hand. The network reinvented it from data. Go deeper and you get textures, then parts, then objects. The feature engineering era ends, and the next wall appears immediately. This thing takes one fixed size image and says what is in it. It does not say where, and you cannot slide it over 100,000 windows.
2013. Ross Gershick and colleagues at Berkeley build the bridge, and the idea is embarrassingly practical. If you cannot afford 100,000 windows, do not look at them all. Run a cheap, dumb algorithm first. It merges similar neighboring pixels into blobs and hands you the blobs boxes, about 2,000 of them. Then, on each one, crop it, stretch it to a fixed size, push it through the network, classify what comes out, and nudge the box to fit. Regions with CNN features. RCNN. On Pascal-Voc 2012, the score jumps from 35.1 to 53.3, the largest single jump in the field's history. It is also a mess. 2,000 network passes for one photograph, 13 seconds an image on the GPU of the day, and 47 once people swapped in a bigger backbone. And 3 pieces bolted together, trained apart. Not a detector, a chain of programs. 2015, and 2 walls fall in 1 year. First, the seconds per image. Those 2,000 crops overlap enormously. You run the same convolutions on the same pixels again and again. So flip the order. Run the network once over the whole image and take your regions as rectangles on the resulting feature map instead. ROI pooling cuts each region out of the shared features and squashes it to a fixed size. One network, one loss, and 47 seconds becomes a fraction of one, which exposes the second wall. Selective search is now the slow part, about 2 seconds on the CPU, and it cannot learn. Faster RCNN's answer? Move the proposals inside the network. A small region proposal network slides over the shared feature map, and at every position considers a fixed menu of reference boxes. 3 sizes, 3 shapes. Anchors. For each one it says object or not, and nudges it. Anchors solved it. They also introduced a pile of hand-tuned numbers the field would spend 10 years trying to delete.
2015 again. Joseph Redman asks why there are 2 stages at all. Why not just look once? You only look once. YOLO. One network, one forward pass, pixels straight to boxes. Divide the image into a grid, 7 by 7 in the first version. Every cell predicts a couple of boxes, a confidence, and a class. All of it as one block of numbers, one loss. 45 frames a second. The stripped-down version, 155. For the first time, general object detection runs faster than video plays. It pays for that. The first YOLO is less accurate than faster RCNN, and bad at small objects and crowds, because a cell only gets 2 boxes. 5 birds land in one cell, 3 of them do not exist. Months later, SSD fixes much of that with anchors and several feature map scales at once. And now, what a one-stage detector actually outputs. A one-stage detector does not emit a list of objects. It emits a dense grid of guesses. For a modern YOLO at 640 by 640, about 8,400 candidate boxes. Every image, always the same number. Each carries 4 numbers for the box and a score per class. The model never decides how many objects there are. It cannot. The output shape is fixed before it sees the picture, which means most of those boxes describe the same dog. So at the end of every detector for 20 years, there is this loop. Sort by confidence, take the best box, delete every remaining box that overlaps it by more than a threshold. Intersection over union. Shared area over combined area. Repeat. Non-maximum suppression. Now look at what it is. Not learned. No gradient through it.
That 0.45 is a number a human picked, and you retune it per dataset. It runs on the CPU after the GPU is finished, and in a crowd, it deletes real people, because real people overlap. Remember this loop. The next big idea exists to delete it.
2016 and 17. Two fixes that become the recipe for the next 6 years. The first is scale. Deep in a network, the features are meaningful, but the map is coarse, so a small object is a smudge. Early on, the map is detailed, but the features are dumb. Feature pyramid networks build the pyramid inside the model. Take the deep features, upsample them, and add them sideways into the earlier detailed layers. Now every scale is sharp and smart. The second is a counting problem. A one-stage detector scores something like 100,000 anchor boxes per image, and maybe a dozen contain an object. Train on that, and your loss is a wall of easy background. Focal loss fixes it with one term. Scale each example's loss by how wrong the model still is, so the easy ones stop shouting. RetinaNet becomes the first one-stage detector to match two-stage accuracy. That is the peak of the anchor era. Backbone, pyramid, anchors, focal loss, suppression. And look how much of that a human designed. 2020. A team at Facebook AI Research asks the question the whole stack had been avoiding. You want a set of objects out, so why are you not predicting a set? DETR, Detection Transformer. Take the image features and hand them to a transformer decoder, along with a fixed number of learned vectors called object queries, 100 in the original. Each query is a slot. Each slot looks over the whole image and outputs exactly one thing, a box and a class, or the special class no object, which is how it says nothing is here. 100 slots, always 100. So the variable length problem from the first minute of this video is gone. The length is fixed, and emptiness is a valid answer. No anchors, no proposal stage, and no non-maximum suppression. That last one is where people get it wrong. DETR does not remove duplicates with a cleverer architecture. It removes them in the loss function. You have 100 predictions, and in this picture, 3 real objects. Before you can compute any loss, you must decide which prediction is responsible for which object. Old detectors answered with a rule. Any anchor overlapping a true box by more than a half is a positive. That rule is exactly why duplicates exist. Many anchors match the same object, so many predictions learn to fire on it, and you need a suppression loop to clean up after your own training. DETR answers it with an assignment problem. Build a cost matrix, 100 rows, 3 columns. Each entry is how bad that prediction would be for that object. Wrong class, plus how far off the box is, plus an overlap term. Then run the Hungarian algorithm, which finds the cheapest one-to-one matching. One call to SciPy. 3 predictions get an object each. The other 97 are trained to say no object. 2 queries cannot both claim the same dog, because the loss punishes the second one during training. The bill? The original DETR needed 500 training epochs and was poor on small objects. A beautiful idea that was not yet practical. So the next few years are spent paying that bill. Deformable DETR finds the cause. Every query was attending to every position in the image, which is quadratic and mostly wasted. Instead, let each query attend to a small learned set of sample points across several feature scales. 500 epochs drops to 50, and small objects get much better. DINO adds denoising training. Feed the model deliberately corrupted versions of the true boxes and ask it to repair them, which stabilizes the matching. Plus, a smarter way to start the queries from the image instead of from nothing. It takes the DETR family to the top of the COCO leaderboard. Then RT-DETR from Baidu, a hybrid encoder that skips expensive attention where it does not pay, and a query selection step that starts the decoder from good guesses. The paper is titled DETRs Beat YOLOs on Real-Time Object Detection, which tells you exactly who they were talking to. The transformer line has arrived at the one thing YOLO was famous for: speed. Which brings us to now. The two families converged. YOLO v6 has one-to-one head and is end-to-end by default. No suppression step, no threshold to tune. What was DETR's headline selling point is now standard on the convolutional side. And rf-detr is a transformer detector that actually runs in real time. Compare them on COCO, the standard 80-class benchmark, and it is a tie. YOLO v6x reaches 57.5 on 55.7 million parameters. rf-detr large reaches 56.6 on 129 million. What still differs is further down, what the backbone learned before it ever saw a box. YOLO's is trained on the detection task itself, on labeled boxes, overwhelmingly COCO-shaped pictures. rf-detr's is DINO v2, trained self-supervised on a huge unlabeled pile, with no detection labels at all. It never learned, this is a dog. It learned what visual structure looks like. Broad priors travel to domains the model has never seen. Task-specific features do not, and you pay for them in weight. Which is why COCO is the wrong thing to choose on. Your data is probably aerial tiles, or defect scans, or ultrasound frames. RoboFlow built RF100VL for exactly that, 100 datasets across 7 domains. These figures are July 2026.
The chain, one more time. Every link is a wall. Sliding windows were too slow, so Viola-Jones made the window cheap. Hand-designed features could not generalize, so the network learned them. 100,000 windows were unaffordable, so RCNN proposed 2,000. 2 stages were too slow for video, so YOLO did it in 1. Duplicates needed a suppression loop, so DETR made the loss 1-to-1. Both families landed in the same place. 1 stage, no anchors, no suppression, end to end. Practically, in 2026, ordinary photographs, plenty of labels, deploying to a small device, take YOLO 26. Far from ordinary photos, few labels, and you cannot open source your code, look at rf-detr. And if you honestly cannot tell, that is fine, because fine-tuning either one is about 3 lines of Python. Try both on your data, not on COCO. The thing worth keeping? Nothing here was invented because it was elegant. Every step exists because somebody hit a wall. Subscribe if you want more of these. One concept all the way down.